For doing the statistical data analysis of your Mentos Diet Cola reactions, I want you to look at, first of all, the difference between precision and accuracy. Precision is how close you are to each data point. For instance, if you look at this paper that I have right here of a game that you might play out in your backyard, okay, you got three rings that are really close together. And that would be really good precision because all the rings are really close to each other. Now, if you look at the definition for accuracy, accuracy is how close the data is to an accepted value. So if you look at this, you'll notice that the three rings are closer together, which gives great precision. But it's not very accurate at all because it's not on the peg. So the peg would be considered our accepted value. This one right over here, sorry about the glare, is neither good accuracy nor good precision because the rings are not close together. That means it's bad precision. They're not close to the peg. That means they're bad accuracy. If you look right above it, here you have one ring that's off to the left, one ring that's on the peg. So you got roughly good accuracy because you got a ring on there, but they're not very precise whatsoever. And then the next one is good accuracy and good precision because they're all close together and they're all right on top of each other. Usually with precision, though, we talk about how much off we are. So we're going to say, plus or whatever your answer is, plus or minus. You might have seen this on presidential polls when they'll poll and they'll say that Hillary Clinton is ahead of Donald Trump by 4 points or something like that. They say give or take or plus or minus 2 points. That's their margin of error. We'll discuss how to get that in just a second. Now, if you're going to do a group of data, like, for instance, you're doing the group Diet Coke versus the group regular Coke, or caffeine-free versus caffeinated, or the flavor of soda, and you're comparing all those. If you're doing group data, let's look at number 2 and 3 and explain how you're going to sort of relate all those together. So I'm going to get rid of this particular screen here real quick. So on number 2, it says to calculate the averages of the controls and the average of the groups of data. So let's just say that you were doing diet. Oh, sorry about that. Let's just say that you were doing Diet Coke. Oh, I can't get my pen to write. This is Diet Coke versus regular Coke. Sorry, I'm trying to get my pen to write, and I got my finger on the. And the answers that I got for this, or the data that I got for this, let's say is 3 meters, and then 4 meters, and then 5 meters. That's a 3, believe it or not. And over here I have 4 meters, and 5 meters, and 6 meters. Golly, this is hard for you guys to read. Now, the first thing it says to do is average these up. So if I'm going to average my controls is my diet here because all these were the same thing over and over again. And you expect this 3, 4, and 5 to all give you the same height, but it didn't. There's some sort of other variable in there that's throwing us off. So 3 plus 4 is 7, plus 5 is 12. 12 divided by 3 ends up giving you 4 meters for the average for this. So anytime I put an X with a bar over it, that means the average. So the average for that first set is 4. The average for the second set, 4 plus 5 is 9, plus 6 is 15. 15 divided by 3 is 5 meters. So you would be tempted to say, well, that regular Coke is higher than Diet Coke because the average is 5 and Diet's average is 4. But you can't really say that because if you just look right here at the controls themselves, there is a difference between 3 and 5 of 2 meters. So you can say on average that the regular Coke is higher than the Diet Coke, but it's only a difference of 1 meter because 4 minus 5 is a -1 or a difference of 1. But since you have a 2 meter difference right here in your controls, which should be identical to each other, you can't say it's the type of Coke, like diet versus regular, that's causing this difference between the 4 and the 5. It just might be a fluke that that's happening. So what we use in math to determine whether a variable is really affecting the outcome of an experiment is something called standard deviation. And standard deviation, if you look at number 3, it says this. Gosh, I'm so sorry, this is bad, hard to write. The standard deviation. That's hard to read, rather. Deviation. I got to get me something to write with. Deviation. All right. What standard deviation says is this. Let's just say we were looking at a group of students' grades. This is the number of students here. And this is all the F's. And this would be D's and C's and B's and A's. Well, you would expect that there'd be a lot of people that have C's, but very few people that have F's and D's. So your graph would sort of look like a bell. That's what we call this, a bell-shaped curve. Okay? Now, what a standard deviation, it says, is this. One standard deviation represents 68% of your data. Why? I don't know. I'm a physics teacher. Okay? Two standard deviations represents what 95% of your data is doing. So let's get an example of this. Let's say that you put your data in your calculator and you found out that the standard deviation for your data equaled 10 meters. Well, if one standard deviation is 10 meters, that means that 68% of your data is 10 meters apart. That's a heck of a lot. So if you're looking at diet versus regular and you saw that your diet versus regular was 10 meters apart, you would know that diet is better than regular, or regular is better than diet, and you knew it for sure because 10 meters is almost 30 feet, if not more. Okay? That also means this. Two standard deviations would be 20 meters. And that's equal to 95% of your data, which is almost all of it. So you could say that, with 95% reliability, that your data is 20 meters apart, which is almost 60 feet. So diet versus regular has a big, big, big difference. Now, if your standard deviation is really small, let's say your standard deviation was only 1. Well, if your standard deviation is only 1 meter, that means that 68% of your data is only 1 meter or about 3 feet apart. That means all your data is really close together. So your variable had nothing to do with, or no effect on your outcome of your data. So let's discuss now how you're going to get that standard deviation. I'm looking at number 3 on your worksheet. I have a calculator up here, and what I did is I went into the calculator and I hit the stat button. And when you hit the stat button, it allows you to go to number 1, edit. And I'm going to put all of my data for all the groups, the diets and the regulars, or the caffeine freezers and the non-caffeine. I'm going to put it all together in one great big old list. So I got 3, 4, 5, 12, 13, 14. I just put it all together. I'm then going to get the standard deviation for that. Now, the way you do that now is you go back up to stat. I'm going to hit the stat button. I'm going to then go over to calc. So I'm going to take my arrow key and go over to calc. And like it says on number 3 there, you go to 1 bars. So I'm just going to hit enter because I've already highlighted 1 bar stats. And it gives you this list just like this. And if you notice, on the calculator, now as soon as I start writing it, the calculator is going to disappear. But if you look down, it says X with a bar over it's 8.5. That means the average is 8.5. The sum of the X's, or the little sigma X, is 51. But if you look at the SX, which is the standard deviation, that is 5. So that means that 68% of my data is 5 meters apart. So I'm going to write that down for you here. So 68, one standard deviation is 68% of your data. Why? I don't know, it just is. But our standard deviation equals 68% of our data, which equals 5 meters. And so I can say, 2/3 of our data, or about 68% of our data, is 5 meters apart. Well, 5 meters apart is 15 feet. That's pretty high. So I would think that whatever my variable is had a big effect on the outcome of this data. Okay, so for all those people doing groups of data, you're going to want to use standard deviation. You can also discuss the variance. So if you go back to your calculator here, see where it has that little, I don't know, it looks like a little fish or a little, something that looks like a little alpha. Hold on, let me go back to this. Sort of look like this, X. That's called the variance. And that tells you how far off each of your data points is from your standard deviation. All right. On number 4, it explains to do a chi-square. I don't think most of you had enough bottles to do a chi-square analysis. Don't worry about that. Let's do number 5 now, which discusses groups that did the number of mentos affect the height of the cola. You're going to want a line graph with these. If you're doing the number of mentos or you're doing maybe temperature, does temperature affect the height of the cola, you're going to use number 5. Let me show you how to do that. Now this next one, I took my calculator and I went to stat. So I hit the stat button. I then went to edit so I could put in the data. And in my first column, I put down the number of Mentos that I put in the tube or put in the bottle. And in my second column, I put the height that it went up. So I got 0, 1, 2, 3, 4, 5 Mentos, and then 0, 0.5, 1.5, 3.5, and so forth as far as the height that went up. You're going to do the same thing, but now you're going to want to get a line graph. So when you graph this, I come over here to graph. Uh-oh, I don't have my graph turned on. I'm going to go second, stat plot, and I'm going to turn on number 1. And I'm going to connect all the dots here using a line graph. And then when I graph it, if you notice, it makes a nice little line. It might be a curved line, but I'm going to just assume it looks like a line. If I zoom in on this, it sort of looks like a straight line. So I'm going to go to stat. I'm going to go over to calc. Once again, I'm following number 5. But now I want to figure out what is the linear regression line equation, I can't talk, for that particular line. So I'm going to go to number 4. And when I hit enter, it now gives me this formula. Okay? I'm going to go ahead and write that formula down here on the screen. The calculator is going to disappear though. Okay? So when I do that, I have y equals ax, shoot, sorry, I keep putting my finger on the screen. Y equals ax plus b. Y stood for your height. So this is going to be my height here. A was my slope. X was my number of Mentos. And B was my y-intercept. So what this was saying is, I'm going to put in the numbers it gave me, that to calculate the height, the slope was 1.4, and that means meters per mento. I guess the singular of a mentos is a mento. So the way I understand, know it's meters per mento is if you look at slope, slope is the same thing as rise over run. And on a graph, you're going to make a line graph here, and your height's going to be up here. So that would be meters. Your mentos is going to be on the bottom. So your rise is your meters. Your mentos is your run. And so that's why I know it's going to be rise is meters per mento. Okay. So that's going to be the slope of a line. And your line's going to end up going something like that, right? Okay. Now, the slope was 1.44. The number of Mentos was your X. I'm going to put the Mentos in there. And then finally, your Y-intercept was a negative 0.69. Well, let's look at what this means. If you put in 0 Mentos, so I'm going to put in a 0 here. 0 times 1.44 is 0, plus a negative 0.69. So what this is saying is if you put in 0 Mentos, you get a height of negative 0.69. Well, you know that's not correct because your Coca-Cola didn't just suck down into the ground when you opened it up with no Mentos in it. So this is now going to become your margin of error. So your y-intercept is your margin of error, which tells you how much your experiment is actually off. And if you're doing the number of Mentos, you need to show the graph and the line of best fit. Okay, I want to show you now how to do the Excel spreadsheet. So I'm in Excel here, and for those people doing groups, I have a little chart over here to the left that says diet versus regular. I just made up some data. And what's great about Excel is you can copy and paste this right into Word. So I just typed in the heights for my diet, the heights for my regular. Then I'm going to highlight the whole thing here. I'm going to take this over here and just drag it down. Okay. Then you go to Insert. Go over to the bar graph, hit the 2-column bar graph, and there it is. Now I can come up here. I can change my title to diet versus regular, something like that. That way you have your, variable on your graph, and there you go. Now, if you're going to do a line graph, like for the number of Mentos, if you notice over here, I put down the number of Mentos and height. You're going to do the same thing. Let me get rid of this graph right here. I'm going to just click it and delete it. Now I'm going to do the same thing. I'm going to highlight it, but instead of doing a bar graph, we're going to go to Insert, and I want a scatter plot. So see this one right here that has all the dots on it? So I'm just going to scatter it, but I want to connect the lines. And so that now gives me a scatter plot. And now you can actually come down here and put titles on your X and Y graph. Now, I'd also like to get a line of best fit, so let me show you what to do there. If I want a line of best fit, I'm going to actually click on the line it made. So if you notice, when I click on it, actually I'm double-clicking it here. I'm going to right-click it. When I right-click it, it'll say Add Trend Line. When you add the trend line, you can then come over here, and it'll ask you what type of trend line you want. At the very, very, very bottom, it will say to display equation. You want to do that. And I also want to display that R² value. And when you do that, you just hit OK. And if you notice, it now has the equation up here on your graph. And the R² value tells you how close your data is to your equation. So for instance, if it's really close to 1, if you notice my R² value is 0.96, that means it's really close to 1. That means your data equation is very reliable, and you can almost predict the height of that Mentos Diet Cola fountain. So once again, make sure that if you're doing the number of Mentos, use a line graph with all the equations like this. And your percent error, or your margin of error, is the y-intercept. If you're doing the groups, then you're going to use a bar graph data. I hope this helps, and good luck.